Okay, so good afternoon, everyone. So it's an absolute honor to have Dr. Beane in our first CoE Statistics seminar in 2020. So Dr. Uding is the Mike and Sugar Barn Professor of Industrial and System Engineering, also Professor of Electrical and Computer Engineering. He is a member of Texas A&M Institute of Data Science, the Energy Institute, and TWS Institute of Manufacturing System. He received his PhD from the University of Michigan in 2001, and his research is in the area of system informatics, data science, and data quality. He is the recipient of 2018 Texas A&M Engineering Research Award, and also the recipient of the 2019 IASE Technical Innovation Award. He's also a fellow IASE and ASME. He recently published a book, Data Science for Wind Energy, and his research activity is supported by many grants, including National Science Foundation, the Air Force Office of Scientific Research, Department of Homeland Security in the state of Texas, and many industry, including wind industry. So please join me in welcoming Dr. Beane from Texas.
Thank you very much, Ramin, for the very kind introduction and for the invitation. It's absolutely a pleasure to come to visit University of Miami. I come to the area many times, and if you live in the United States, you cannot avoid Miami, right? But this is my first come to on the campus. Nowadays, the data science is kind of a topic you cannot avoid, so that's something I want to talk about today. And I'm glad Ramin mentioned about the book I last year published. And because the talk primarily based on the second part of that the book, it's 4 chapters, and I will briefly mention that toward the end of that. But one of the central themes we talk about today is the so-called gray box of machine learning. We don't really particularly talk about box, but I want to give that kind of philosophical understanding. And people said when you have this kind of models, which is based on physical law and so forth, so you know how the things kind of go in, how it's manipulated, and how it goes out, and the meaning and the rhythm of that. And really, they call this kind of a white box system, right? And then nowadays, a lot of this kind of data-driven method, especially like the deep learning things, right? You have some kind of thing going inside, and then you have the data going outside. And the machine learning mechanism or algorithm is so complicated, and the parameters so numerous, and so numerous you even couldn't count them. I'm not talking about tens or hundreds or thousands. It could be hundreds of thousands or million parameters in the deep learning black box, and then you don't really know how this kind of things being manipulated eventually give you a result. And we only know in some of the instances, actually, they are reasonably or they are astonishingly successful, right? But many of us working in the engineering field there should be kind of some compromise in between. There probably should be a kind of physics-guided or physics-informed and the type of machine learning, the type of knowledge people accumulate over the hundreds of thousands of years, and how that kind of knowledge should be transformed into that kind of machine learning process. And so that is something called gray box machine learning. This is really kind of the so-called gray box. It's not really invented by me. The phrase has been around for 20, 30 years. It's just in the recent data science era, and in the so-called artificial intelligence, people sometimes feel the human stupidity sometimes still relevant. Okay, and that things is the knowledge, and in the mathematical term, more kind of come through a constraint. Now I want to kind of share with you on some of the thought along that line, based on our own work in the wind energy, how we apply the data science for the wind energy part. That's why the book was called Data Science for Wind Energy. Okay, so before we get to the data science part, I want to take one step back to give you a little bit kind of history about the wind energy part, right? If you go to Wikipedia, the earliest recorded history about human civilization use wind energy is going to that Roman Egypt time. I'm pretty sure people actually use wind energy even before that, but they probably don't have a record, right? If you go to the Wikipedia, they said this is the Harris wind-powered organ is the first kind of recorded this design, right? They hung this the wind wheel, which can be driven by wind, and then kind of driven this music organ can play a music for you. It's almost like a old music box of that sort, right? But when we talk about windmills, and the first thing pumping into our mind is almost like this, right? The medieval part of Europe has all these kind of windmills and everywhere. You still can go to, especially like the outskirts of Amsterdam, to visit one of the wind farms to see those kind of things about the 400 years ago. And as a matter of fact, 2017, when my family and I was vacationing in Amsterdam, I took my family over there, visit one of the wind farm. My daughter, she was 8 years at the time, was very excited, and she thought this is the very cute windmill daddy is working on. And 2 days later, we were in downtown Antwerp. The downtown Antwerp has this harbor with a very wide river. On the river side, on the other side, there was a small wind park, and there was industrial scale, modern style wind turbines. And I told her, actually, this is the wind turbine Daddy works on, and not the one you saw 2 days ago. And she was very disappointed. She thought that Daddy really got the priority all messed up. Okay, but for a very long time, the wind turbine doesn't really produce electricity directly. They don't really, because before microfarad and invented electrical motors, we don't really have that kind of conversion, right? So the windmills are actually driven directly a kind of mechanical work. Be it milling, cutting, moving some things from one place to another place, moving water from one place to another place. And after 1830 something, when the electrical motor was invented, and then people come to realize you can actually use that kinetic energy, convert that into the electrical energy, and then you can transform the electrical energy to a far away place for it to be used. So the first electricity generating wind turbine actually was built in United States, not in Europe. In 1887, 1888, around that period in Ohio by Charles Brush. Okay, and he built this wind turbine. This is a still very ancient looked wind turbine, and they operated that the wind turbine for a number of years. Eventually was bought by Thomas Edison's General Electric company. Okay, and that combined company eventually evolved into today's GE. And that probably explains the GE's invested interest in wind turbine technology, and also is one of the leading wind turbine manufacturer worldwide. There are three big ones, right? Outside China, it's GE, Vestas, and Siemens, right? And then today, China's Goldwind is probably another one, kind of rival to the other three big turbine manufacturers. So now the wind energy has not been taken seriously for the most part of the time until roughly about 40 years ago, right? 40 years ago, after the war in Mideast, there was the OPEC country imposed the oil embargo on the Western society and lead to the first global oil crisis. And then people start looking for the renewable alternative. So the reason more kind of energy conscious society was not the first time, right? It was what happened before. At that time, wind energy is one of the energy form has been contemplated. And people thought for every kind of knowledge behind the wind energy generation, we know that, right? They primarily come from aerodynamics and construction engineering, because the wind turbine structure is huge. So you need a lot of this kind of know-how from civil engineering to build those kind of large structures. Okay, but of course the wind energy, how do you convert that wind flow to electricity? That kind of basically driven by the principles in the aerodynamics. So we know all these kind of knowledges, and the company said, why don't we just build a bunch of them and start producing the energy? And so there's a long list of the companies in the early 1980s, in the late 1970s, actually try their hand. And the problem is that none of them succeed at that time. And there's a serious underestimation of the complexity in this wind turbine, specific the technology, especially in terms of the cost effectiveness, right? They can produce the energy, but it probably doesn't produce the energy, the typical customer want to buy, right? It's not really kind of very competitive in that sense. And the kind of scale up, if you think about the propeller from the helicopters, and when you scale to that kind of 5 megawatts wind turbines, that's a very big scale up. That size is kind of a very different kind of order of magnitude. Yes. Okay, thank you, sir. So what's the solution? And eventually the Denmark scientists said, okay, if we cannot build very large wind turbines, why don't we kind of take one step back and start with something small? Okay, so the very first wind turbine they built and successfully produced wind energy at a more kind of economical scale actually is 10 kilowatts, about 10 meters in diameter, right? This picture I show over here actually started with 17. So the one they built started with actually is even smaller than that. But even 17 in diameter actually is not very small compared to our typical perception of size, because this is the typical size of a house, right? You have a kind of residential house is about 3 to 4 meters high, okay? And then you have a 17 in the diameter, this hub height is probably about 20 meters high. So that thing actually is pretty big already, okay, if it's next to your house, okay? And, but over the year, they learned these things from that small scale wind turbines, and then the human nature, driven by curiosity and accumulation of the knowledge, and make the turbine bigger and bigger, okay? And this is kind of the journey in the past about 35 years. Okay, the largest wind turbine nowadays is still under construction, not under operation yet. Is this Haliade X GE wind turbine? It's offshore. It's a near shore offshore, right? It's still very close to the land. It's a near shore offshore. And how large it is the tip side here is 853 feet tall. Okay, and that is only about 200 feet shy of this Eiffel Tower, about 60 meters difference. And make the wind turbine nowadays one of the largest rotation machinery on Earth. Okay, and people said, what is the big deal about that? Right? We have structures even taller than the biggest wind turbine, but they don't have any kind of large things to kind of rotate on their head, do they? And that actually makes the whole thing complicated. Once you have this kind of rotating things, this dynamics generated on top of the hub, and that makes the whole thing more complicated. Okay, and with this large scale deployment, also the building of large size turbines, and you can imagine the electricity energy supplied by the wind power actually grow quite impressively over the past 20 years. In year 2000, the electricity produced by wind energy is only 0.15%. Okay, it's roughly about 0.1%. But last year, the last year's data this is estimate because they only have the data through the third quarter of last year. But it's estimated close to 7.5%. Probably a little bit less than that, could be 7.2% in the end. Okay, and it's also the first time the installed capacity of the wind turbine exceeding 100 gigawatts, and in terms of the generation capacity. There's only one country is more than what US has in terms of the wind energy producing capability. It's China. And China has roughly about double. They have about 180 gigawatts installing capacity. But the capacity factor is a little bit lower. So in terms of the actual producing wind electricity from the wind source, it's just slightly more than the US. It's not like the double of the US, the electricity produced. Okay, so in about 2008, about 12 years ago, the US Department of Energy issued a white paper. It's called 20% by 2030. So it's a kind of a positional paper envision, how the wind energy will play in the national landscape in the next number of years, right? And that white paper has been updated over the time. And then the ambition is try to produce 10% by 2020, 20% by 2030, and 35% by 2050. Okay, and that goal is very ambitious. Actually, the first goal, the 10% by 2020, we are 2020 now, right? We are January 2020. And then the energy estimate production of the electricity in 2019 is only 7.5%. And the year before was 60.8%. So over the year, the increase is less than 1%. So how much we can expect from now to the end of the year, it can increase 2.5%. For the entire United States, the energy increase, I mean, not the increase, the wind production increase 2.5% of the entire nation's electricity consumption. That's a huge amount. Okay, that's not a really small deal. So the very first goal probably is going to be missed. It's going to be missed. But we are not really too far from that goal. Right, we're still close to that goal, right? Probably by the end of the year, it's going to be 8.5%. And so the question is how far we can catch up in the next decade to the 20% by 2030. Now, if you think about this kind of numbers, especially like 35 by 2050, that's a very ambitious number. If you have wind about 35% of the electricity, produce 35% of the electricity, you're going to have solar produce a similar amount, okay, in the long run. Okay? And if you have wind and solar produce about 60% of electricity, you have nuclear about another 20%, and then you have hydropower another 15%. You only have 5% of the electricity you need to produce from oil and gas. Okay, and the rest of the things can. So it's not that if we ever achieve that time. The so-called renewable to provide most of the electricity used in the nation is by and large accomplished. Okay, but that's really a very long way to go. One of the reasons for the renewables, especially for the so-called variable renewables, primarily the solar and the wind, is the issue of the subsidy. The wind company used to be heavily subsidized by the federal government. In the form of the PTC, the production tax credit. A couple of years ago, right, the PTC is about 2.3 cents per kilowatts. And you thought that is not too much. Actually, it's a lot. Okay? And if you, in the electrical market, you should think about this number of 5 cents per kilowatts. Usually, if you can produce electricity about 5 cents per kilowatts, you're almost guaranteed to make money. I'm talking about wholesale, right? If you go back home, you don't pay 5 cents per kilowatts. That's a bargain, right? You pay about probably double that price, okay? The wholesale market is, if you can do like 5 cents per kilowatts, you are doing fine, right? If you produce electricity more than 7.5 cents per kilowatts, you're probably not going to survive long, right? In between, it kind of depends. Okay, this is a long-term average. In the short term, like in the very hot summertime, of course, sometimes the electricity market can go up to like 50 cents per kilowatts, right? But that is a short period of time. Okay, if you have an average cost, the cost of energy is 6 cents per kilowatts for the onshore wind, and if you give them 2.3 cents per kilowatts as the tax credit, and then that really kind of give them the advantage to be competitive, right? But over the past years, over the current administration, well, this is not really said by the current administration. Actually, was said even before the current administration take their position. Is the wind PTC was phased out, okay? And the initial deal is like they are entirely phased out from January 1st, 2020. Okay, in the very last maneuver, if you remember seeing the news in the middle part of the December, the Congress passed this kind of the spending bill. Okay, and within that bill, there's one provision to extend that the PTC by 1 more year. Okay, and what Congress is going to do for next year, we don't know yet. Okay, and they could possibly extend that for another year. But what the PTC works is, they give you the PTC, right? As long as you start constructing wind farm in year 2020, you will enjoy that PTC for next 10 years. Until 2030, the wind farm will still receive that credit. It's just for whatever the new construction start next year, they don't have that benefit anymore. Okay, but nevertheless, right? Once you stop the PTC, the subsidy, you're going to have some kind of effect on the wind energy production. But nevertheless, as my professional society is in industrial engineering, and one of the things we care about is really kind of the performance and efficiency and so forth. And to us, it's not really feasible. You're going to subsidize the industry forever. Sooner or later, right? I don't know when it's going to happen, who is going to do that. the subsidy is going to go away. This is not only in United States. Even for environmental conscious Europe, they start changing the incentive plans. They start reducing the incentive to renewables, okay? And because they want the industry to stand on their own feet, okay? So one of the key issues, of course, is really kind of the boosting the wind energy market competitiveness. And in order to do that, there's two important questions. And one question is you want to quantify the performance, right? You want to know who is doing better, who is doing worse. And therefore, you can select what is the best practice, identify the so-called underperformance, right? And then, therefore, to make the corrections. And the second thing is, suppose we have a certain kind of physical mechanism and other things, control mechanism, can help us to kind of enhance the performance. Because the wind industry, the wind turbines and all these kind of things are heavy asset investment. It's like you put wind turbine over there, you spend a lot of money up front. It's a capital cost. It's not like, next 5 years you can just unroot all the wind turbines and put a new one over there. So over the time, you needed to kind of boost the performance, right? So one thing we noticed, there's not a lot of research along this line yet, because the wind turbines, the wind industry is a relatively new industry. And one thing, if you study reliability, you find this is the typical so-called bathtub kind of reliability curve, right? You start with the so-called infant fidelity things, which you convert, you flip the side. You have the initial kind of increase of your performance, and then have a plateau, a very long stable period, and then you have the end of the service, you basically kind of lost the efficiency. But one of the paper published in 2014 to indicate the production efficiency for the wind farm have very small, very narrow, this kind of stable operation period. And then before they have this kind of rapid decline, the end of service life period, they already see a noticeable decline over the period of their typical operation. Okay, because the wind turbine subjected to very non-stationary load, and it's coming down fast, slow. It's not entirely controlled by us. Okay, and it's also standing in the wilderness. Okay, and then how do you that kind of things make the wind turbine deteriorate faster? Okay, and so the performance quantification, performance evaluation, enhancement, they are become very important things. Now, people said, what is the data science here? Why data science played a role over there, right? So data science played a role, and this is the kind of the bridge kind of connect the data science part with the turbine performance. So one of the things people in the industry standard to use to quantify the performance of the wind turbine as a whole, not as an individual component, is use something called the power curve, right? The power curve has the wind speed as the input and has the wind power output, okay? And this is something called cut-in wind speed. This is called cut-out wind speed. So when the wind speed pick up to a certain kind of value, like 3 meters per second, and then the wind turbine start producing, right? And then they producing more and more to some kind of the capacity level, and they use a kind of control mechanism to level off the production. And this is called the rated wind power. This is called rated wind. This is rated wind speed. This is rated wind power. And then it kind of plateaued over there. When the wind speed is really, really strong, and they're going to shut down the wind turbine. Sorry, to make sure it doesn't endure any kind of mechanical damage. Okay, and that is called the cut-out wind speed. I think, okay, well, let's back on. Okay. So this is one of the industry standard to say in order to quantify that things, they use something called production-based availability. It's basically how many power output you observe and compare with how much you expect, right? The actual industry standard is a little bit more complicated than this equation, but because that is not really the focus of the talk, so let me just kind of use this simplified version that is easy for us to understand. So the question is, how do we estimate this wind power curve? I think I damaged this. Okay. So the industry recommend you use something we call the Beane method. It's a non-parametric method. It's very simple, okay? And the method works like this way. You collect the data from the input and output, right? And then when you plot this one, you find there's a very noisy data over there. And what they does is they don't try to use any kind of equations. They just cut the data into different beans, typically with a bean size of 0.5 meters per second, okay? And then for each bean, if you magnify that, this is one bean, and they take all the data, fall into that bean, take a sample average, okay? And then they use that sample average to represent how much wind you get in as the input and how much you expect as output. And then they use a smooth line to kind of connect the beans together. So this is called Beane method. And the industry like to use this one. Actually there's a data science justification for that. It's a non-parametric method. It doesn't rely on a lot of assumptions, okay? And even you have different kind of make and model of the wind turbines, they can always work, okay? And the process is so simple, people knows exactly what goes in, how the data is manipulated, and what comes out. Okay, and it also computes very fast. It doesn't really have a lot of computational power in order to do this kind of analysis. But there's a number of data science challenge, and even for handle this kind of estimation of the power curve, right? Because what we see here is basically just a baseline process. And for this Beane method, it only handles one single input, which is wind speed. But in reality, in the wind power production, there's more than one single input affecting the wind production, right? Not only the wind speed, the wind direction, the air density, the humidity, the other things will affecting those things. So I list the 6 of them. Actually, if you have possibly the measurement, it could be more than 6. But even if it's 6 of them, suppose you only use the Beane method. The Beane method basically just kind of localize every data point and for you to do estimation, right? And if you have one dimension, and if you cut everything in 20 beans, suppose you have one whole year of data, the industry usually like to arrange the data in 10 minutes block. So for 1 year, every 10 minutes data give you about 50,000 data points, a little bit over 50,000 data points. So you have 20 beans in one dimension. For each bean, you're going to have 2,500 data points. That's many enough for you to do average, right? Suppose you have 2 dimensions. You have 20 beans along one dimension, 20 beans along another dimension. And then you're going to have 400 beans. And then you have 50,000 data points. You're going to have, how many is that? So 50 divided by 400, right? It's going to be a little bit over 125 data points per bean, right? So suppose you have 125 data points, still is okay. If you have 3 dimensions, okay, and then every dimension has 20 beans, you're going to have 8,000 beans. Okay? If you have 5 dimensions of the input variables, each variable has 20 beans, and how many beans are you going to have total? You're going to have 3 million beans. Okay? And every 60 beans share the data. You don't have, on average, every bean has a data point anymore. So how are you going to do the average? There's no much way you can do the average. So that's one of the, it's a very simple math for you to handle this kind of thing. That's why usually the Beane method doesn't really scale very well. It doesn't really kind of, if it's only have one input, the Beane method and other method give you more or less the same result. If you have 2, you can handle that. 3 is probably you are stretching it. 4, people actually stop using it. Okay, so that's the thing, right? So one of the solutions we use is to use one of the machine learning method, or actually it's a statistical learning method. It's a kernel method. But even the kernel method also run into that kind of scalability problem. And what we handle that issue is we use this kind of hybrid model. We use this kernel method, but we only limited that input as a 3 input. Right, and if you probably heard about the so-called generalized additive model. And this is more or less kind of in that kind of thought. It's a generalized additive model, but different from generalized additive model. The typical generalized additive model only has every term as one input. The downside for every term has one single input is you lost capture the interaction of the inputs. Okay, so this is a kind of better trade-off. You have the 3 inputs into one element. Therefore, you limited whatever the dimension you run into, no more than 3. Okay. On the other hand, when you have more inputs, what you're going to do is you're going to add more terms. Okay. It's not really the perfect model, but it gives you kind of better interaction between these 2 things. And the reason we use the kernel because they can do the mean prediction, they can also do density prediction. So give you a way of quantification. Because if you, for example, predict that this is your average performance, it also gives you this distribution and how much you have this kind of uncertainty. You can quantify that. The next things we realize for this kind of power curve problem is things related to the autocorrelation of the noise of the data. Okay, because the data comes in kind of time series way. Okay, and when you have this model, suppose a simple model like this, and then you have the error term, and oftentimes we assume the error term is IID. When the error term it is indeed IID, like in this figure. And you can use the regular cross-validation to select the right model and the parameter of your model. And eventually, your estimate model give you an unbiased recovery of the true model. Okay? And that is typically what we learn in our machine learning class. But when you epsilon has autocorrelation in them, and this is not true anymore. Okay? And actually, if you use a regular cross-validation, you select the model, they oftentimes are biased from that true model. Because we know, in this particular case, we know the true model because we run the simulation. We know what model to start with. And now we purposely added the correlation over that, and now we use the regular cross-validation, like the 10-fold or 5-fold cross-validation. You select the model, which is the model parameter. This coefficient is not 2 anymore. Okay, it's kind of shifted. Okay, and that gives you a wrong estimate. And the danger not only in terms of the parameter, sometimes they will select overly complicated model, which is called overfitting, right? You all know the terminology. And then the model actually was warranted. Okay? So one of the solutions we try to handle that things, we haven't published a paper for this one yet, but we are close to, is we needed to handle that kind of temporal structure in the data. So what we do is like for 1 year data, we kind of chop that into certain kind of temporal block, okay, or seasonal block. Within each block, we split into further cubes, okay, and to allow us to do a cross-validation with the temporal structure in place. Okay? And then once we do this kind of splitting, what we're going to train this model is this part we assume is not really kind of depends on that correlation part. The other part is related to the correlation. We need to select this fx, which is independent of the time, out from the part related to time. So how you would select the model structure, which is independent of the time? You're going to train with this kind of blue cubes of the model. And now you're going to test on the other cubes. And now you're going to train on the green cubes. And then you test with other cubes, and so forth. And then you do all the things. When you average that, they give you much better selection of the fx is independent of the time than the selection I just mentioned before with the regular cross-validation. And then once you select this part, of course, you can take a difference between the actual observation of the fx. You get a residual which is autocorrelated. And now you can use some kind of either Gaussian process model or other time series model to handle that kind of the temporal correlation, and usually only happen in the temporal vicinity, right? If this is whole year data, that g of x usually is only about a few weeks, and then afterwards you don't really have much autocorrelation anymore. Okay, so this actually helped us to do this kind of handle this model selection part. Another part to speak more kind of how the physics understanding. The other part has the physics understanding into that. But this part has a more direct connotation of the physical understanding. So when we're doing some of the model with the physical understanding, we don't necessarily know the exact the physical law governing the underlying process. But oftentimes we have a notion, if this thing's kind of always going up, is this always kind of positive, and those kind of things. And that can be translated into a set of constraints. And usually we call it the size or shape constraint, right? One of the things one of the methods used the so-called shape constraint happen in data envelope analysis, which is part of the technique in the production economic analysis, right? If you study some of the industrial engineering courses, and the production economic analysis actually said, suppose we want to evaluate a firm and we want to compare with different firm which one is more efficient. And the notion says the firm D is not very good firm because with the same kind of input, the firm E actually produce more, okay? Or by producing the same thing, the F actually use less. So the so-called efficient frontier is really on this kind of out layer of those data points, okay? But in order to kind of estimate that kind of frontier, and the economists actually postulate the frontier need to be concaved, okay, and monotone, okay. But for the wind turbine data, we can borrow that kind of thought, but there's two things different. Number one, the wind turbine data is not noise-free. If you look at this one, right, all this kind of data point was passing through by the efficient frontier. And that is not really the good strategy if we handle the wind turbine data. And what the wind turbine data give us is something we call the stochastic frontier analysis. Because you need to handle the kind of random noise. This deviation is due to the random noise. The second thing is, if you look at the wind turbine power curve, right, and here, they are not really kind of concave or simple convex. Actually, they are S-shape. They start with a convex shape and then followed by concave shape and connected by inflection point. Okay, and the reason for that is really because of a turbine control mechanism. The physical law says the energy being generated from the wind turbine generally, if it's not controlled, will increase in the convex fashion, in the cubic fashion. But because of the so-called pitch control law and other kind of control law, and which eventually bend this curve to a concave curve and to a plateau. Okay, and this kind of curve is in fact pretty widely used in economic analysis. It's called the marginal return on investment. Right? If you think about human population increase, right? They initially kind of increase very, very slowly and really kind of pick it up. When there's a lot of people, eventually it's going to slow down again because the entire Earth's resource is limited, okay? And the large company, you know, when they, like a Google, when a small company, they kind of grow very fast, but it's not going to grow like that rate forever, right? And then eventually they're going to plateau. And the same thing for the wind power curve. And there's a shape constraint over there. Now, there are also a kind of sign constraint, which is a positivity and negativity, right? There's something unique in the wind farm analysis is called the wake effect. When we said this turbine is on the downstream wind from the first turbine, we said the turbine 2 is in the wake of turbine 1. Because once the wind has, part of the energy has already been picked up by turbine 1, the energy intensity is lower when it's hit turbine 2. So the production efficiency for turbine 2 will be smaller than turbine 1. So that's why it's called in the wake. And when the turbine is in the wake, they always try to quantify, you know, how much you have the wake loss. Okay, and that affects the prediction and also the layout, the design for the wind farm. So the model basically says, suppose you have a common frontier of your best performance. Okay, and then your actual production is that frontier minus the inherent inefficiency and minus this wake effect. Okay, if you take the difference between these two models, you find this is the difference between these two turbines. This is the efficiency difference between these two turbines, and then this two wake effect. Now, this difference can be positive or negative because we don't really know which turbine is more efficient. But the wake effect is always positive because we use the negativity in front of that, or at least it's always non-negative, right? Of course, their presence and absence is decided by the wind direction. But in order to solve this kind of problem, you have to make sure those kind of constraints to be part of that data science problem. Okay. Now the issue. Okay. So we talk about a number of the data science issues, and we do have some of the solution to that. And then we come back to that power curve. The wind energy issue again, right? So how this kind of power curve modeling can help with the decision-making process. And the help with the decision-making process, one of the application area is help to us to quantify. If someone said, I have one of the mechanism which can enhance the performance ability for the wind turbine production, okay? And remember this curve, right? If we have some kind of way to do a turbine upgrade, and then to make that kind of decline, which counteract on that part, and it's a good thing, right? So one of the technology being invented for doing that is something called Vertex Generator. This is one of the sample of the Vertex Generator. It's not a very large thing. It's about the palm size. It's entirely plastic. Okay, the particular design actually make a difference. And so this particular wind turbine Vertex Generator is designed by Smart Blade. I happen to work with this company, right? You need a bunch of them. The single Vertex Generator doesn't really work that well. So you need a bunch of that. And what you do is you put on the wind blade. And the promise is once you put over there, actually you can increase your turbine's performance, even it's a kind of aging turbine. Okay, and but in this material cost is not much, right? It's a plastic, and you can readily make those kind of things. But the installation, in order to do this Vertex Generator installation, you're going to stop the production. Not only for this particular turbine, you need to stop a bunch of turbines nearby because otherwise it's kind of dangerous for someone to climb up. So the general cost is about $10,000 a turbine. If you have 200 turbines in a wind farm, in order to have all this kind of upgraded, you are looking at $2 million up front. Okay, and is that worth it? That's the question the wind operator constantly asks them. Once I put over there, does that give me the enough return to justify the investment upfront, right? So there's a advertisement. Actually, I taken this from the internet, and this is EDF is one of the French wind company, right? They teamed up with 3M. The 3M is also partner of Smart Blade because Smart Blade is a very small company. They have their R&D office, and which is basically just one room, right? Because the whole company has less than 10 people. I've been to their office and pretty much interact with every one of them. And so they don't really have this kind of infrastructure to reach out to many different kind of markets. So they team up with the 3M. They also use the 3M glue on the other side of that Vertex Generator, right? You peel up the things that just put on the blade. And they need to make sure they stay on the blade. Otherwise, after windy night and all the Vertex Generator is gone, you lost the benefit, right? So the 3M make a very strong and practical glue to be used with the Vertex Generator. The Smart Blade team up with the 3M. So in this advertisement, you don't really see Smart Blade. But if you magnify, this one is not clear for you to see. If you really magnify this one large enough, you will see their brand name over there. Okay? So their advertisement basically said, if you use my technology, you get an AEP increase, 1.5 to 3% increase, you get your money back in 1 or 2 years. Yes, ma'am?
How big it is?
This Vertex Generator is about palm size. You need to put like a 10, 15 along the ridge of the blade. Okay? They have a particular design for that. Okay? Okay? So is that claim true? Okay? Now, we did actually a simple calculation. If we have all these kind of assumptions, 200 turbine, 2 megawatts class, and if you can sell the wind energy at 6 cents per kilowatts, which is a little bit kind of overestimate, and 3% improvement, it gives you about $1.2 million actual income. Okay, so if that's the case, their claim is about true. Okay, so the question is how much the installation of the VG can give you actual energy. Okay, and that actually becomes a not so easy answer to question, because the general consensus is usually it's between 1 to 5%. Okay, but if you look at the wind data, it's very noisy. Okay, in order to detect about 1% difference in that kind of noisy data, and how you can be sure of that detection. Okay, that is the tricky question, and therefore we have to use a lot of heavy machinery of the data science part. We haven't used the deep learning yet, but the other things we try to give us kind of credibility in answering that question. Right? One of the things people said, why don't you just compare the input, the two turbines, the output from the before and after the installation, and the reason is really because the input cannot be controlled. Right? This is different from the gas and oil and gas turbines. You put this much fuel inside. You can measure that with precision, and then you see which one produces more energy. You cannot put this much wind into your wind turbine, and so your wind is changing. So if we put the distribution of the environmental condition before and after the installation, you find they don't match. They don't match, right? So you don't really know how more energy afterwards is because of the wind blow harder, or it's because of the VG actually played a role, right? The industry actually, I think there's something happened to this controller when I dropped that. So why this power curve model can help? The power curve model is basically mathematical surrogation of the physical reality. When we train in the first step, when we train the model, it's almost like we take a picture of the old turbine, okay? And then we kind of recorded how the turbine performed in that model. And then the second step, when we feed the new environmental condition to this power curve model, it's like we're running this old turbine under the new environmental condition. And then we do a comparison between this old turbine supposedly run on the new environmental condition and the actual observed the power you kind of collected on the new environmental condition. And that difference to give you some kind of understanding, whether or not this is something you can attribute to the installation of the VG. But the idea is not difficult, but the actuality, there's a number of complexity we have to handle. The industry, when they do this kind of comparison, they don't really kind of just simply use one turbine. They realize there's a lot of other kind of random effect. So they usually use a pair of turbines, right? You have a test turbine, which VG was installed. There's a control turbine, which VG was not installed. So you have this kind of 4 pairs of the data, right? The XO, because the turbine is so close, so you can consider the input is more or less the same. The output is not exactly the same because the 2 turbines, 2 independent turbines. And after the installation, the Y new test and Y new control definitely cannot be the same, right? And the difference between that, presumably to tell you something of the VG effect. There's another technique actually commonly used in social study because they cannot do controlled experiment. So they use the observational data. But because of the observation data, sometimes it's apple and orange. It cannot be exactly compared. So what they do is they select a subset of data. The statistical probability are very much comparable in terms of distribution. And now once they have the subset of data, they compare the effect. So the same idea can be used here. It's called the correlate matching. The correlate is the X. So we have the data. We said, okay, the X have a different kind of distribution. Why don't we select a subset of X such that their distribution is the same? And then we compare Y, okay? And the idea, of course, works. But there's a subtle problem about the bias part. There's a kind of threshold you can tune to say how tightly you can control the matching of the distribution. If the distribution was compared very, very tight, you don't have much data left. If you give some kind of allowance, you're going to run into some kind of bias problem or the residual bias problem in the end. So what we do here is we want to demonstrate that residual bias by using a simulated study. The simulated study basically said, suppose we forgot about all the test turbine data. We simply use the control turbine data, duplicated exactly the same data as the test turbine data. Okay? If you apply any kind of method to this 2 pair of data, 1 pair of data, 2 turbines, you're supposed to see a 0% because these 2 sets of data are identical. Okay? If you don't see a 0%, there must be something you are missed. Okay? And we can also artificially increase the energy rate for the artificial part of the test turbine part, and then to see how much we can recover that percentage point. So when we do this kind of simulation study, we find this correlate matching actually has roughly about a 2% bias. So they cannot, if we very, very tightly control the threshold, we don't have much data left. If we don't control, we control to the level we're comfortable with, we have about 2%. But what is the size of the difference we try to recover? It's also about 2%. Okay? So that's the problem we run into. And in the end, we have to use together with the test turbine and the control turbine. And this is a little bit kind of busy slides. But the general idea is really try to estimate that confounded effect of the other change happen to the turbine from the control turbine part, and then to decouple the VG effect and the one you try to uncover. And by using this combined method, and we were able to recover that bias. This even on the simulated study, they give us a much accurate estimate of the VG effect. Okay. Of course, some of the method works for the simulated data. It don't necessarily work for the real data. And so this is also a company's concern. They want to know whether or not your method, you truly know what I'm talking about, right? So the way they design one of the tests is they want to do a kind of blind test. They give us 3 sets of data, and there's some turbine probably being upgraded, but they didn't tell us which one. They didn't tell us how many, but they did tell us if the upgrade had happened and which day the upgrade had happened. So that separation point they told us, but they didn't really kind of provide additional information. And they want to know, how our algorithm find out the upgrade. Okay, it's very hard to directly test on the upgrade quantification, but they can at least detect the presence of the upgrade. Okay, so we applied a method to the 3 tested turbine. We tell them only the 3rd turbine has been upgraded. That's the only turbine has been upgraded. And it turns out we actually answered that question correctly. And otherwise, we're probably not going to hear from them anymore, right? So that was a good thing. The part of the story we discussed actually was summarized in the chapter 5, 6, 7, 8 in the book we just published. The data and the computer code actually was made available online. And you can go to this, the CRC Press's website, and you can also go to this book website to download the data. You don't have any obligations to use the data. So it's entirely free. And we also have 2 R package. This kernel plus is for the multidimensional power curve model, which is really the core of the method. And also the GAN ML. This is a name suggested by the company people for the VG effect quantification. Okay. Do I have a few more minutes? Okay. So I want to get back to the original things I mentioned about this data science and demand science relationship, right? I want to tell you a story about how I come to think about this issue. And I worked with Brian Hayes, which is the executive vice president of EDPR. A lot of this kind of study actually is working with our company. And he eventually became a good friend of mine. And one time we were having breakfast together, and he asked me whether or not I have read this book, Moneyball. I said, I haven't. I heard about the book, I heard about the movie, but I'm not a baseball fan, so I didn't really spend time reading that. He said, you should read that. Yeah, please make sure you read that. So I bought the Moneyball. I didn't watch the movie, I read the book. Okay, and just in case you don't really know the story, the Moneyball actually is starting with this statistician. His name is Bill James. And he, in the 1970s, started publish so-called Bill James' statistics of baseball. Okay, and nobody paid attention to him. Nobody in the baseball field paid any attention to him for a very long time. The argument was very simple. He said, who is Bill James? Does he play baseball? No. Does he even watch baseball? Perhaps, right? So why should I, as an expert, to hear someone telling me what to do about baseball from people just know data science, doesn't know demand science, okay? And then it comes this person, Billy Beane, okay? Eventually become general manager of Oakland A's. And Billy Beane actually was a star athlete in high school, okay? At the graduation of high school, he has a choice. He can either go to Stanford University to get a college degree and also become student athlete, or he can sign up directly with New York Mets to make money. And the temptation become a star athlete with New York Mets actually is hard to resist. So he chose to sign up with New York Mets. But his experience actually made him regret that direction ever after. And he was a failure as an athlete himself. And whatever other people said about him, the promise they said, the kind of prediction they made on him, said he will be the next Babe Ruth. It didn't come true, not even close. Okay, and then he, after a couple of years struggling with the New York Mets, he decided quit. He quit the baseball career, playing baseball career altogether. He eventually take a very low position with Oakland A's, and eventually rise up to the general manager. When he became general manager, he said, there's something wrong with how people use the data in baseball field. Okay, you are not really paying attention to the right data. You probably even didn't collect all the data you should have been. He hired an economics graduate from Harvard, helped him to run this kind of data crunching algorithm. He disregard those kind of baseball expert has been telling him who he should recruit and how his strategy should play out. Okay, and he made a number of these very unconventional buys, use very little money to buy a player nobody wants, and yet put them in a position eventually pan out a result, in a very impressive way. Oakland A's, when Billy Beane was the general manager, was able to get into playoffs in consecutive years, yet spend the money only a fraction of the other Major League Baseball teams. Okay, and then eventually people couldn't really kind of ignore that effort, and that is basically the starting of the sports analytics. If you nowadays you go to any kind of sports, not only baseball, basketball, football, which player goes to which position is not decided by human entirely anymore. It's really kind of decided by human together with a data crunching program. Okay, and the story here, is like, the data science used to be ignored altogether, right, by demand science, expert, it takes quite an effort eventually for people to come to realize the importance of the data science. Okay, so next time when I was having lunch with Brian Hayes again, I said, Brian, I read the book. You are my Billy Beane. And he said, you are my Bill James. Okay, but on the other hand, one of the things I want to come here to talk today is when the data science is playing an important role nowadays, we need to be in the humility to understand data science doesn't solve everything. Okay, we cannot really do without the demand side. So we cannot be too hubris to say data science can do, pretty much replace the human, right? Not yet, maybe one day. But I still believe for engineers, for people study in the engineering college, and the best solution is still blending the data science and demand science. And we need more pairs of the Bill James and Billy Beanes because they appreciate each other. Okay, and they actually function the best when they are together. Okay, thank you.
Seen recently what happened with sport analytics and the collecting of data. Two managers just got fired.
Oh yeah. That's an ethical issue about the collecting data.
I was also interested in the slide you showed from 3M. I happen to be working with a company that supplies tools for the people who are climbing the tower.
Oh, I see.
Okay, and in some of the towers they have inside steps to walk up hundreds of feet, carrying 50 pounds of tools. So there are a lot of practical problems in the maintenance of the wind turbine. Not just building them and make them efficient, but they have to be fixed every once in a while. It's a major issue.
Right. That's a very good point. Thank you. Yes, ma'am.
I thought the analysis of the environmental data was very interesting. And what I found really interesting is that you have a control to compare your new turbine to.
Right.
What if you didn't have the control? Would you still be able to use a similar?
Well, that's a good point. Actually, in the book, we do dedicate one paragraph to say, for the model alone, if you look at the industry practice, if they don't have control, they cannot really do anything. But when the model is possible, it's not ideal because there's a lot of drifting and shifting, so you can get something, but probably not as quality as you have a control turbine to do with it. Okay, so that confounding cannot be completely decoupled. You're going to have to suffer some of the bias over there. Okay, and not only that, the game ML package we released, actually the company insists to put 3 turbines to work. There's another issue because of this so-called wake effect. This is the wind speed actually is measured right now on the wind turbine after the wake. How unscientific that practice is still the measure of the turbine is measured after the rotor. When the rotor is the aerodynamic characteristic is changed by the VG, the wind speed measurement actually is changed. A turbine, with 5 meters per second free from wind before the installation of the VG, after the installation of VG, the measurement on the anemometer on the turbine is different. And that difference is not very large, but it's large enough to change 1 or 2 percentage points. Okay? And that's why the company using that technology insists to use a different kind of neutral turbine, which the measurement, even it's biased, but it's not affected by installation VG. And that sometimes doesn't work for the small wind farm. The small wind farm, they don't have much wind turbine to start with. And even they are kind of spread out. Right? In this case, you need the wind turbine pretty close to each other, like a few hundred meters away.
So even the control has to be controlled.
Yeah, even the control has to be controlled. So that's kind of the delicate issues because of even 1% is not much. It's enough to tip off this kind of investment, right? Yet they need to have some kind of certainty that 1% is really 1%. It's not like negative 1%. Yeah. Yes, sir.
Is there any possibility that they could test within a controlled environment so that?
Not anytime soon. Yeah, because the size of the wind turbine don't really allow the controlled experiment to do that. They did that in a small-scale lab test about 25 years ago. They said if you install a VG, you're going to see 25% of increase of the production efficiency. No, not even close. If it's 25%, we don't really need all these things. You can easily see the difference, and then it's no brainer to install that technology.
The question is about the size of the bandwidth in the method, in the averaging method. Are you fixing it or are you optimizing it?
Optimize it. You need to kind of, that's one of the things that we said when the epsilon is autocorrelated, so actually they tends to choose the wrong bandwidth for you.
Sorry?
When the epsilon is autocorrelated, they choose the wrong bandwidth parameter for you. So yeah, so that has to be carefully chosen and how the way you do the cross-validation. And therefore you can handle the bandwidth. That has a big impact on the final quality of the model. Yeah.
Okay, so unfortunately we are running out of time.
Thank you.